Hey guys, today I'm going to talk to you guys about nuclear fission. First of all, I'm going to give you guys a brief introduction to nuclear fission, and then later on, I'll give a brief explanation of what's in store for the future of nuclear fission. What is the process of nuclear fission? Nuclear fission is the process of one atom splitting into two or more other atoms, releasing some energy and other decay products. This energy has been locked into atoms for billions of years from the atom's creation in hypernova. This happens under its huge gravitational force and is held together under the strong nuclear force. For example, in the fission of uranium-235, the uranium's nucleus is excited by the capture of a neutron and splits into two nuclei, giving each nuclei roughly half of the original total mass. A typical fission reaction is shown below. What does fission look like? A generalized picture of the process fission goes through is shown below. As we go along, we will go into more detail on what happens further into this process. Why is nuclear fission interesting? What is really fascinating about nuclear fission is that it releases huge amounts of energy compared to other sources like oil or coal. The reason for this is that pure uranium has a much higher energy density than most sources. What is energy density? Energy density is the amount of energy that can be stored in a given mass of a substance or system. Therefore, if we have a higher energy density in that system or material, we will have a greater amount of energy stored in its mass. To give you an idea of how much bigger uranium's energy density is than other fuel types, a table for you is shown in the next slide.
When a nucleus receives a thermal neutron but does not undergo fission, it releases gamma radiation as its nucleus relaxes. However, over 75% of the time that uranium-235 nucleus receives a thermal neutron, the uranium atom will undergo nuclear fission, typically splitting into a krypton and barium atom, three lone neutrons with 179 megaelectron volts of energy released. The reason neutrons are emitted relates to the line of stability of atoms. The line of stability is a best fit line of the number of neutrons to the number of protons for which any given atom is most stable. As the typical fission products are typically neutron rich and far off the line of stability, neutrons are spontaneously emitted from the fission products, allowing them to decay to a more stable form. The fact that this fission reaction produces neutrons opens the possibility of a positive feedback loop of fission reactions, where each fission reaction produces neutrons which drive a new fission reaction, whose neutrons drive a new fission reaction, and so on. In order for a fission chain reaction to occur, a threshold of fission reactions must have the necessary energy to produce the fission fragments. The critical energy can be viewed as the barrier of the Coulomb force between the two fission products. A fission reaction will only proceed if the energy supplied is greater than the energy required to bring the fission products to within such a close radius at the time of splitting. Note that for uranium-235, the critical energy is about 6.2 megaelectron volts, which is less than the 6.5 megaelectron volts supplied when the uranium-235 atom absorbs the thermal neutron. Thus, the excitation of the uranium-236 atom is enough to force the uranium atom to split into constituents. The fact that uranium-235's excitation energy is greater than its critical energy is what makes it a viable option for fission plants supplying nuclear power.
First clues of the possibility of fission. In 1919, Ernest Rutherford, the same person who performed the gold foil experiment, became the first person to both deliberately transmute one element to another and split the atom entirely. By bombarding nitrogen with naturally occurring alpha particles from radioactive material and observing a photon emitted with higher energy than the alpha particle, this gave him a clue that the nucleus was made of several smaller pieces that could be subdivided. This is also when nitrogen was transmuted to oxygen, changing the element entirely. Him and his colleagues were also the first to deliberately split the nucleus. He did this by using a particle accelerator to accelerate protons at high speed into lithium. This created two alpha particles in the process. The first fission of uranium-235 was done by Otto Hahn and Fritz Strassmann in 1938. This earned Hahn a Nobel Prize for his work of carefully studying what happened to the uranium when it was hit by the neutrons. He found other lower mass elements being produced. It was later discovered that the reaction also produced more neutrons in the process, leading to the speculation of a chain reaction and nuclear power. Using the power of fission. Soon after Hahn's discovery, Enrico Fermi proved nuclear power was possible when he made the first nuclear power plant in 1943 called the Chicago Pile 2. This used uranium oxide and uranium metal as fuel, and at its peak generated about half a watt of electricity for 9 years. Naturally occurring uranium needs to be mined right out of the ground like any other minerals. Then to extract the ore, it is dissolved in a strong acid that dissolves the uranium right out of the rock and other impurities. This process creates uranium oxide, often referred to as yellow cake uranium for its color here. But the uranium that comes out of the ground is not ready for use. 99% of naturally occurring uranium is the 238 isotope, and when it gets struck by a neutron, it eventually decays into plutonium, emitting some electrons, antineutrinos, and gamma radiation, but it never emits more neutrons. U-235, however, when it absorbs a neutron and eventually decays, it creates 2 to 3 more neutrons, allowing the process to continue. Therefore, the naturally occurring uranium has to be enriched to contain more of the U-235 isotope. But the only physical difference between the two isotopes, besides their fissionability, is their mass. Therefore, most enrichment is done using centrifuges that take advantage of this difference. But for the centrifuges to work, they require a fluid material, so the uranium needs to be combined with fluoride, creating uranium hexafluoride. This makes the uranium a fluid gas at low temperature, making it easier to separate than a solid. The uranium hexafluoride is then put into centrifuges to separate the two isotopes. More of the heavier U-238 is thrown to the outside by the centrifugal force, while a more concentrated amount of U-235 is closer to the center as it feels less of this force pushing it out. Then it is extracted by essentially a vacuum sucking out the gas closer to the center. The now enriched uranium needs to be converted further, this time into uranium dioxide pellets that are then put into fuel rods packed closely together so the chain reaction can occur spontaneously. But to keep the fuel rod from melting down before it even gets to the reactor, we need a way to control the reaction. Therefore, control rods are used, as they are made of a material that will absorb most free neutrons that strike it. They are placed in between all the fuel rods to essentially stop the reaction to a standstill. Essentially, this thing would slide in here, into these holes. This is how the temperature is controlled. The more control rods down, the slower the reaction, the less heat being produced. The most common reactor in use today is the pressurized light water reactor. This shares many of the same basic principles of most other reactors in use today. The fuel rod assembly would be in one part. The control rods can be lifted up, allowing heat to be produced. This heat in turn makes steam. This steam drives a turbine. The turbine in turn drives a generator. And then the hot water is allowed to rise in the cooling tower and condense back down to be reused. Nuclear bombs work essentially the same way as a power plant. The reaction just needs to happen a lot faster. Therefore, nuclear bombs and the nuclear fuel must be enriched to a level near 90% fissionable material to get the explosive reaction wanted, not just a lot of heat. For a nuclear bomb, essentially you just need a big ball of fissionable material, usually 235, but with the material separated in some way that is not at a critical mass needed to explode. So long as the critical mass is not reached, it will just sustain the reaction slowly without increasing its rate. The critical mass is determined by a number of things, such as density, temperature, enrichment level, shape, and most importantly, its mass. To detonate a nuclear warhead, the uranium must be brought together quickly, combining them together into large enough mass so that the chain reaction is not just sustaining, but exponentially increasing. As seen here, a detonator would shoot some of the uranium-235 into another pile of it, and that would make it reach the critical mass needed. An analogy of this would be trying to start a fire with the wood scattered all across the ground. Trying to light any one piece will be difficult and it will quickly burn out, but if you bundle all the wood together into a type of critical mass, then the fire can easily grow.
Here we have a picture of thorium and also the atomic number of thorium. And it brings us to the section of why thorium is the future of nuclear fission. It is important to know that uranium isn't a renewable source, and although we have predicted we have hundreds of years before we run out of uranium, it is important to think of the future for safer and better ways to make nuclear fission work. One of these things is thorium. Thorium is a naturally occurring, slightly radioactive metal discovered in 1828 by the Swedish chemist Johannes Jacob Berzelius. Sorry if I mispronounced that. How is thorium better and safer from uranium? Thorium is 3 times more abundant than uranium, produces less waste, and can't melt down in its new reactors. The reason it can't melt down in its new reactors is because liquid fluoride thorium reactors are designed to be meltdown proof. A plug at the bottom of the reactor melts in the event of a power failure or if temperatures exceed a set limit, draining the fuel into an underground tank for safe storage. Another reason thorium is safer is because thorium reactors' plutonium production rate would be less than 2% of that of a standard reactor. Even though it's only 2%, this is still very important because scientists say plutonium could be the worst of all the fission byproducts. Here we have the atomic number of plutonium and also a picture of plutonium to give you an idea of how it looks like. And it brings us to the section, why is plutonium considered the worst? Plutonium emits alpha radiation rather than beta or gamma. External exposure to alpha particles isn't a big health risk only because they have low penetration depth. When they are dangerous, though, is when alpha emitters get inside cells, then they can become extremely hazardous because when they are sent out from within the cells, they can cause anywhere from 10 to 1,000 times more chromosomal damage than beta or gamma rays. Although thorium has many advantages, like most things, it also has a disadvantage. The only real downside of thorium is feasibility of processing fuel. Ratan Kumar Sinha, my apologies if I've pronounced that name wrong, the former chairman of the Atomic Energy Commission of India, explains by giving the analogy that thorium is like wet wood. It needs to be turned into fissile uranium just as wet wood needs to be dried in a furnace. What he means is that thorium is not fissile on its own. Thorium fuels, therefore, need a fissile material as a driver so that a chain reaction can be maintained.